Hello, everyone. This is Discrete Math 2020, Fall 2020. Today is Class 5A, which I have clickbaited as to infinity and beyond. Okay, yes, I am going to mention infinity and stuff like that, but it's clickbait. What I'm really talking about today is the natural numbers, the integers. So I've already defined the natural numbers. I'm going to go ahead and talk about the integers and things like that. And my headset. There we go. So yes, as I said, it's a little bit of clickbait. So, but we will talk about it. So, about the test, I saw the scores that were very good. I hope you guys are pleased with them. A couple of things that I saw of the binomial theorem. You got one of them, but not the other, right? You couldn't identify which one was the simplified binomials, or, a good half of you, a little bit less than half, like a third of you couldn't. And that binomial theorem is going to come back again and again and again and again and again. It's sort of the center of a bunch of the number theory, and we're starting to get into the number theory. And the binomial theorem connects things in calculus, if you care about that, to this idea of counting things, of just, counting mixes and subsets with a bunch of the number theory. It's like, it's one of those things that connects several areas of mathematics, right? Sort of like the fundamental theorem of algebra connects calculus to polynomial algebra. The binomial theorem is one of those kind of base things that lives at the bottom of a bunch of stuff. And then it comes back, and every time you see a thing, you're like, oh, that's the binomial theorem. Oh, that's the binomial theorem. Oh, that's the binomial theorem. And believe it or not, RSA and Diffie-Hellman, which are these two huge computer security protocols that have been around since, 70s and so on, are dependent upon the binomial theorem to work. So I really, you have to get the binomial theorem in this class. It's like one of the major themes. And so you're going to see it come back again and again and again and again. I haven't read through the surveys yet. I know you guys are taking them. If you haven't done quiz 5A yet, I think I left it open. If I didn't, I'll go back as soon as, for some reason, Canvas isn't letting me in right now. It's like every time I get an authorization error. I tried clearing my cookies and all that, and that's annoying. What's the binomial theorem again? So the binomial theorem was that thing where a plus b to the n equals, n choose 0, a to the n, b to the 0, plus blah, 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 blah. It'd be, a plus b to the n equals that thing. What is a set? Yeah, okay, now you're trolling me. So those are things that kind of, they're really important, and I want to get to them. Also, I got a new screen. The double screen I had before was making me sound a bit like a robot. I don't know if this one will fix that, but if it's just like, I sounded like a walkie-talkie. I don't know if this will fix the thing, but hopefully it will. So those are kind of the big things from the test. I was very pleased with how well you did on like card counting problems and getting the definitions and stuff like that. But, the stuff about the binomial theorem was one of those red flags for me. I don't think I asked it. I don't think I emphasized it enough to get to make sure that you guys would understand it, because it is kind of one of the fundamental things. Most of you got that question, but some of you didn't. A good third. So we need to fix that. Otherwise, I was very happy. I hope you guys are happy. And as I said, I'll look at your happiness later when I see the scores. Let me see here. I also got this thing, which is supposed to go on my glasses. Speaking of cool new toys, I got this thing that's supposed to go on my glasses so I could see the chat. And still like pay attention to everything else, but it's sort of, it works a little bit, but it's not. It makes me look like a giant tool, which may be appropriate, maybe I am, but I don't think it's worth the additional, the fact that I could see the messages in here sort of it wasn't useful enough to justify how ridiculous it makes me look. So, it made me look Borg, and that was annoying me. So we'll try to find that if everyone's used that. Okay, so the last test, yes. So let me actually mention this briefly. The test was out of 100 points. Now, Canvas, it doesn't suck. I mean, it replaced Blackboard, and Blackboard was really bad. This was way when I started at USF. So, cell phones had been invented, but not much more, right? We were still walking around with pagers when I started USF. And so the system it replaced is much better, but Canvas doesn't allow you to do certain things. So Canvas doesn't allow you to make a test that's auto scored out of have 110 points on it, but then make it out of 100. Now, I get around that on the quizzes by having that last question. That's the essay question. What did you remember about the last time? I have that be out of 0. And then she puts in a 1 for it. So Canvas will let you bypass it if you manually grade things. But if you have things that are automatically graded, it won't let you do that. So what I had to do was I created an assignment, the one that actually counts. There's 2 places your test scores are in Canvas. One on the test itself, and then what you took, and then once in like an assignment that says the test that counts, which is actually in there. So the one of them's in like the makeup quizzes folder or whatever. It doesn't count for anything. And the other one's in your test folder, and it's out of 100, not out of 110. So that's how I fix that issue, but it's kind of complicated. Okay, will you be able to see what you got wrong? Yes. So I will enable that after everyone's taken. I've got some excused makeups that still have to go. After the excused makeups, I will enable that feature. Okay, so enough about the test, enough about that. Let's talk about what we're going to talk about today. And you need this stuff because the problem set, I was supposed to do this lecture last Thursday, but you guys wanted a test review, so I accommodated that. But you need this stuff to do the problem set, and I want to get to it all today. It may be Thursday before everything's in, but the problem set 5, it's 5, yes. 5 is up. There is no 4. There is a 5, which asks you to implement some of this on the computer. So in order to do that, we have to talk about that stuff. So let's talk about it. So today, great. Today, Reflector's not working. There it goes. Okay. So today, what we want to do is we want to talk about, I don't know why it's like not having the top. It's like not showing the top of the window for some reason. There it goes. Okay. So today what we want to do is we want to talk about, we want to introduce number theory. Now, we're almost to this book. Okay. So this book, we're almost to the number theory sections in this book. So our goal for modules 2 and 3, we're going to do some proofs that are like number theory. So some of the stuff that we're going to do in this book and in whatever version you bought, we're going to kind of mix the number theory with the proof techniques. So we're going to do proofs, but we're going to kind of, we're going to do them at the same time as we do the number theory. We're not going to like separate. We're not going to have a huge section on proofs. We're just going to kind of do the techniques while we do the number theory. So we're going to move a little bit more slowly through the number theory, but we're also doing proof techniques at the same time. So that's why. But we're almost to that book. We need to like finish off a couple more things so that we kind of merge into where the book kind of expects you to be. And then we'll do a bunch of number theory in there. Our goal is to get, so our ultimate goal for modules 2 and maybe 3, I didn't make it on 2 last time. They made them on 3, is to do two major things, ultimate goals. The first of these is what's called Diffie-Hellman key exchange. And the second of these is RSA. This one right here, Diffie-Hellman's actually the more important one in one sense. RSA is, of course, important and all of those things, but Diffie-Hellman in one sense is the more important one. So we're going to be doing a number theory, but we're going to be doing it in with these goals in mind. So we're going to do Caesar ciphers, Vigennet ciphers, which I always mispronounce the guy's name, but he's French, so I don't care. And my last name is French, by the way, so you know. My family got kicked out of France for being Protestant. So, you know, now I'm very down on the French. But Diffie-Hellman key exchange, RSA, we're going to do a bunch of different cipher techniques. And to do that, we need something called modulo arithmetic. So that's where we're headed. I can never spell the words arithmetic. I think I actually spelled it here. Yes. Okay. So we want to head toward marginal arithmetic. But in order to do that, we kind of need to think about how a computer thinks about regular arithmetic. So that's kind of today's goal. We're going to talk about arithmetic. Now, are there any questions about that? I for some reason, as I said, the thing that makes me look like a tool did not really work out. So I can't see questions while I'm talking at the same time. The dual screens, I do have dual screens, but the problem is that I'm looking at one of the screens often to fix things, look at my notes, look at the stream status, make sure everything's still functioning. One of the reasons why I keep making small arithmetic mistakes is because there's just too many things going on at the same time. It'd be great if I had a TA in the room with me, but of course I can't do that because of COVID. You know, if this was a regular production thing, I'd actually have the TA in the office with me. This works very well, and Noah is doing a very good job, but it's difficult to do this all at once here. And now the chat window just disappeared. One of the docs there is chat. Back. There we go. Okay, so, and then all your stream chat for some reason isn't showing up. That's annoying. Okay. So arithmetic are things like adding and subtracting numbers. So let's look at this. How does the computer deal with numbers? Okay. So recall the natural numbers. Okay. 0 is a natural number. So 0 is defined as the empty set. Okay. 1 is defined as the set containing an empty set. And 2 is defined as a set containing the empty set and a set containing both the empty set and the set containing the empty set. In other words, 0 equals the empty set, 1 equals a set containing 0, and 2 equals the set containing 0 and 1. Okay. So for any n, n equals is defined as the set containing 0, 1, 2, 3, ... n minus 1. Okay. How do we feel about that 1 to 5? So what I'm asking, do we have okay. So I define n minus 1 recursively. So I just define it as, okay, so for some reason I don't have a TA punching numbers today. So n minus 1 is the one preceding. But that's a good question. What is n minus 1? Well, let's formalize this. Okay, so, and this is called, so this is the construction. of n. Oh, by the way, someone had told me that there weren't enough women on the side here. Well, the problem is that, women weren't really allowed to be on the side here until the 20th century. But one of the people who came up with the stuff that we're talking about today is Kathleen Booth, who basically invented assembly language. And she's still alive. So, these numbers are getting kind of close to the present. And this is the first person that we've had, not only who's female, but who's actually still alive. She's English. She's 90 something. She's 98 or something. Yeah, she's still alive. You can look her up, Kathleen Booth. Anyway, so this is the construction of n. So this set n, so we find this in a certain way. And our goal today is to do addition and multiplication like a computer thinks of it. Okay? So this is Peano's approach. Okay. By the way, let me just do infinities as an aside, since I did clickbait it. Okay. So I define, for any natural number, I define each one is the set containing it, right? So let me define my first infinity. Omega is the set of natural numbers. 0, 1, 2, 3, ... forever. Which equals n. Omega plus 1 equals the set containing omega. Omega plus 2, and that's an omega. And so on and so forth. And these are called the ordinals, if you care. And one way to define infinity is to say infinity equals omega. Now, it's important to note that when I do infinity, and again, this is just an aside, when I do infinity, there are a bunch of different ways to talk about infinity. So really, when I talk about infinity, it depends what you mean by that. In calculus, we think of infinity as direction, unbounded with a direction. Whereas you can think of infinity as an ordinal, the thing that's after you do all of the natural numbers, you then have a number called the set of natural numbers. Okay, well then omega plus 1 is the set containing the set of natural numbers, and it's not omega. It's it should be noted that it's omega union the set containing omega. Would I write that? What I want is 0, 1, 2, ... And then at the end of the ... I want something called omega. So I want omega to be the end there, just like these. So that would be omega. That would be this set. Right, so this is omega union, the set containing omega. And this would be omega plus 1 union, the set containing omega. Okay, so that's one way to define infinity. Right. So just like n equaled the set containing everything up to n minus 1, right? So 2 equaled the set 0, 1. Well, omega plus 1 is the set containing, well, all of the natural numbers, omega, and omega. So in one sense, and let's get back up here, this is actually interesting. You see these unions? We didn't have unions before. But I could also define n as the set. So using unions, I could define 0 as equal to the empty set. 1 is equal to the set, right? 1 is equal to 0. 1 is empty to the set containing 0. And then 2, I'm going to define as 1 union the set containing 1. So 1 was 0. And then the set containing 1, I'm going to union that. 3 then is equal to 2 union 2, which equals 0, 1, 2, right? Because 2 equaled 0, 1, and now I'm unioning it with the singleton 2. Okay? 4 would equal 3 union the set containing 3, which would give me, now 3 was 0, 1, 2, and now I've added 3. Yeah, so each set for n is defined as the set n minus 1 union the set containing n minus 1. But that means that I can define infinities this way, right? Omega, I define as the set of natural numbers. So that's a new one. Right? I can't define omega like that because that's a first ordinal. So I define that as the set containing 0, 1, 2, ... And remember, I have to assert this set exists. Right? I can't prove that that set exists. It has to be a axiom. Right? I can't prove it. There are plenty of good axioms where I say that there are plenty of good mathematical systems. They're not very powerful, but they're good, where I don't say that this set exists. Okay? And as a matter of fact, I can assume that that set doesn't exist and do math with it, with that set of assumptions. It's just not a very powerful system in terms of what I can do things with. Okay? And then I just define omega plus 1 as equal to omega union the set containing omega. So it's going to be 1, 0, 1, 2, ... But I continue on forever, then cut a comma, and then I have an omega hanging out. Right? By the way, this is called the Trans-Finite Step. So I can go to infinity and beyond. I just have to assert that this set exists. I can't, without that, I can't prove that this set exists without asserting it. Remember, we had those axioms for finite sets, that any finite union existed, and this is a finite union, right? Right, but I haven't asserted that this set exists. There are a bunch of others too. Am I in the way? This is called the Trans-Finite Steps. And I don't know that I don't know. So these are axioms, right? These are the things that I'm assuming to be true. I'm assuming that the empty set exists. I'm assuming that the union of any, I'm assuming that for every set, there is a set containing only that set, right? What have I assumed? I've assumed that the empty set exists. I've assumed that for every S, for every set S, the set containing S exists. In other words, I've said there exists a set called the empty set, and I've said for every set S, there exists a set T such that T equals the set containing S. If you really want to write it in nice first order logic, that's basically I've said, and then for any finite set, for any ST that exists, S union T exists. Those are the things I've kind of assumed. And I'm not going to ask you about this on a test, but that's kind of what I've done. But I can't from that system get here. I've also assumed a couple of other things like reflexivity and a bunch of other stuff that we're just going to like not mention, because I've asserted that if S equals S, then S equals S. Or I'm sorry, I've asserted that if S equals T, then T equals S. Those sorts of things. So those are boring. And they aren't true. I don't know that they're true. I'm saying that these things are true. I'm going to assume these things. Okay. Well, let's get back to this. So how do we feel about this union symbol as a construction? 1 to 5. How do we feel about that? That I can define 4 as 3 union the set containing 3. That's what I mean by that. Okay. All right. So someone's asked the question, so really if n minus 1 equals 6, that's really 7 minus 1. Well, 7 minus 1 is 6, but that's not really what I mean here. What I mean is that the predecessor, and let me clarify that, okay? So the reason why I care, okay, the reason why I care is because a computer can go to the next number, okay? So we can connect math to the way a computer works. And this is what Booth Kettig, which he invented assembly language. This is kind of the thing. Because if you code in assembly language, and no one does anymore, well, some people do, but the assembly language is so high level that you might as well be coding in C almost. It's just kind of a different thing, right? It's not like assembly language, if you don't know, is something that lets you get really big close to the processor. You can actually issue commands straight to the processor. So it's very, very powerful. And C, if you program in C, it'll let you throw in assembly language while you're doing it, which is kind of cool. It's one of the things that makes C so powerful, but it's also what makes it so difficult. That and pointers. So what we're going to define is something called the successor function. Okay, I'm going to define it as follows. For any natural... By the way, here the S meant something different to here. So I'm going to define this thing called sets, successor function. For any natural number n, S of n equals n union n. Okay. So s of 0 equals 1. S of 1 equals 2. S of 2 equals 3. And so on. Okay? And this is how a computer thinks. A computer adds 1. Okay? This is something that a computer to do. I can have if you want to use a Turing machine model, I can have a Turing machine run the successor function, right? It defines, okay, so I've got one spot here on the tape. What I'm going to do is move right one spot and call that number 2. All right. How do we feel about that 1 to 5? Okay. So all I'm doing is I'm going up 1 point. 1 number. But this is how I define what it means to go up by 1 number. Okay? If I wanted to implement this in code, what I do is I want to increment. This is called the incrementer, I think. Right? So what I do is I do k plus plus, or plus plus k, depending on what you want. But if you're wondering why C is called C++, this is why. And this does not, so people say that this calls the +1. It depends which language you do, but incrementation is something that's one of the basic, if you go into your processor, it's one of the things that your processor does, right? Right? It does value +1, but it's not plus. It's important to remember that it's not value +1. That's the effect, right? But what happens is that it sends an instruction that goes increment, which is different than adding 1. The effect is the same, but adding 1 is something a little different. Okay, but to do this, we need a little bit more notation. Okay. So, for any function f and natural number k, define f to the n of x as equal, and I should say for any x in the domain, and any natural number k, define f to the n of x as the following. F of f of f of f of ... of x. And then I need 1, 2, 3, 4. I need dot closures. 1, 2, 3, 4. In other words, f circ f circ f circ f ... f of x, where there are n f's. Right, by basic function composition. So I apply f n times. Right, and then f0 of x is defined as just x. So I don't do anything. If I give f to the 0 of x, I just say that's just x. Okay. So how do we feel about this 1 to 5? This is notation that just means I'm going to apply f n times. For a function exponent. And I want to get it's not really an exponent, it's a superscript, right? I'm not doing an exponent, I'm doing a superscript. It doesn't mean it, right? One of the things that I absolutely hate, warning, this is different. Okay, so the notation sine squared of x from precalc is wrong. Okay? In precalc, sine squared of x equals sine of x times sine of x. And that's not here. Here, sine squared of x, and I would never use this notation, ever, would be defined as sine of x. Okay? I don't even like to use this notation in my calc class because this notation sucks. Okay? The notation for sine squared from precalc is wrong. Means totally different. So by superscript, I just mean the thing up there. I want to emphasize that. I'm not multiplying. This is not multiplication. Right? This is a repeated application. Okay, I don't want you to get stuck by that. Okay. So now, how am I going to define addition? So with this right here, I'm going to define addition. Okay, that embed has to stop. That's driving me nuts. Can someone make that embed go away? There. Sorry, it's like blinking in my eyes. Okay. So for all of you on Twitch, in Discord chat, someone posted a big, when I said warning, posted a little ambulance thing, GIF in Discord, which was really distracting. It's okay. I encourage you to get the enthusiasm. I just needed to delete it. Okay, so addition for a computer. How am I going to do this? Well, what I'm going to do is I'm going to define a function called add. And this is going to be a function from n cross n to n. Okay? So it takes, this notation means that it takes an ordered pair of integer. It takes an ordered pair of natural numbers. And outputs a natural number. Okay? So that means that n with the two lines means the natural numbers. I think I'm going to have to add that to the thing. Notation. N is the natural numbers. 0, 1. And for us, the natural numbers do include 0. I know that's a little weird for some of you because you're like, it doesn't include it. Well, it depends what you define as the natural numbers. What we're going to define, what other people say in, is we're going to call posents because we've got another word for that. So for us, we include 0. Some people don't. Most languages, most computer languages, the kind of default is to include 0 as a natural number. Like in PHP, you do an array. The first index is not 1, it's 0. There are languages that are written so that it's 1. Maple is a good example of one. But for most computer languages that are C-like, it's 0. Java, PHP, C, C++, those sorts of things. I think even Basic. I haven't programmed in Basic in years. That was the first language I learned to program in, and I think it had 0 as the first index by default. Anyway, this function add is going to take a pair of natural numbers and output a new natural number. And the way it's going to do this is this, okay? So this is going to map nk, the ordered pair nk, is going to output to suck to the successor function sk of n. In other words, I take n and I apply s, the function s, the successor function, k times. All right, now let's do an example. Add of 3, 2 equals, well, what I'm going to do is I'm to take 3. Here's 3 on the number line. Right? I'm going to take 3, and then I'm going to apply the successor function twice. So the first time I apply the successor function, I get the number 4, right? So this is going to be s squared, or I'm going to use the word squared, but remember, it's not multiplied. This is going to be the successor function applied twice to 3. Well, that's the successor function of 4, which equals 5. So the first time I moved here, and the second time I moved there. How do we feel about that 1 to 5? Another example, add, if I input the numbers 2, 3, what I'm going to do is I'm going to take 3 applications of the successor function to 2. So 3 applications of the successor function to 2 is the same as 2 applications of the successor function to 3, which is the same as 1 application of the successor function to 4, which is the same as 5. So I'm going to start at 3, and I'm going to go, I'm going to start at 2, and I'm going to go 3, 4, 5. Well, let's do another one. Let's do add. I'm doing these in the right order, right? I said in first, yes. So I'm going to do add 0, 2. Now let's do 0, 4. Well, that is going to equal 4 applications of the successor function to 0, which is the same thing as 3 applications of the successor function to 1, which is the same thing as 2 applications of the successor function to 2, which is the same thing as 1 application of the successor function to 3, which is the same as 4. Please stop saying binomial theorem in chat. It's gonna mess people up. Okay, well, what's add for 0? That is going to equal 0 applications of the successor function to 4, which is the same thing as 4. That's an S, by the way. All of these are S's. That's a 5. That's an SS. SS. That's a 5. I should have used, normally I would use SUC, but I didn't want to do something that was different than what you find online if you go to the successor function. If you go to the successor function online, it says S, so I said, okay, that's fine. Well, then how do we write code for this? Yeah, so here's a fact, but that's not a thing. This is a theorem. I would have to prove this, and I'm not going to because it's tedious. It's not that tedious. It just requires induction. So we will prove this later once we get induction. I think we will. And this is one of the problems with the book. Okay, so people are wondering, I did read a couple comments about not using the book. One of the things that the book does is it does induction early. And I think it's one of the harder concepts. It's not to say that you can't do it. It just requires you to have been thinking about this stuff for a little bit in order to get it. So this book goes through and it then proves stuff like this. We can prove it later. I just don't want to prove it now. I want to wait to do induction later when we do recursion, because induction and recursion are directly related to each other. And we want a little bit more time thinking in this abstract language before we throw that out. But we will prove this later once we get induction. But the theorem is this. Add of nk equals add of kn. Again, we're not going to prove it now. We're just going to say, isn't that obvious? Recursion actually isn't. I mean, it's hard, but it's simple. So I kind of try to make this distinction. Someone said that recursion is hard in chat, and it is. But it's also, it's one of those things like that proof of the binomial theorem I get. Once you see it, you're like, oh, duh. And you feel stupid about yourself for not getting it. No, it's hard. A lot of these concepts are hard, but simple. So I don't want to tell you it's easy. I don't want to do that, but you can get it. And it's not some, once you get it, you're like, why didn't I get that before? Which is very frustrating because it's hard. That's why you didn't get it before. But I want to wait to do that because it's hard. I want to kind of wait until we've played with this a little bit more. I want to make it a little bit more natural when we get there, right? If you've been thinking about these things, it'll be a little natural when we get to it. Okay, so anyway, back to what I need to be talking about, except other than my teaching philosophy. So we've got this thing. Now, the only reason I mention it now is because someone mentioned it in chat. Now, how does a computer do this? Well, it turns out that on your problem set this week, see, relation, the problem sets matter, the problem sets are related. It turns out that in your problem sets, I've actually implemented this piece of little code in PHP for you. Now, obviously, PHP has the addition function already built in. It's called an operator. It's one of its like primitive things that's already built in. But what I've asked you to do, that's calculus. That is how to teach side mount, scuba diving. We're not doing that either. That is the other class. I got 3 folders called classes in my thing, right? Because I got scuba classes, calculus classes. Well, let's pull up our old... I don't want to pull up the key. Let me make sure I'm not pulling up the key. I am pulling up the key. Let's close the key. Okay. All right. So without showing all of your information, let me share screen. Apparently there's no sound. Hold on for a moment. All right, sound is back. Sorry about that. Okay, so what I want to do is I want to pull up add here. And add I'm going to define. Let me go back. Not that one. Okay. There's too much technology going on here. I may have said this before. I don't have techno fear. I have techno joy. Like, I love technology and playing with stuff, but I probably should have it because I'm not apparently very good at it, or at least, things don't go right. I should be a little bit more technophobic than I am, apparently. So if you pull up the problem set, let's do that. Now, okay. So I've implemented this add function in here. So this is how we're going to get the computer to do this. We're going to do something called a while loop. And then we're just going to keep going with the successor function. So we're going to start this kind of incrementer at 0. And then you've noticed I put in code so we can see what the thing is doing. So if I go here to, discrete math, problem sets, and I execute this little piece of code, watch it not work. Right? I've asked it to add 6 to 4. So what it's doing here is it's starting at I equals 0. It declares that. And of course, it's echoing what I've told it to. And now it's going to take n and it's going to add k to it by calling the successor function k times. So here, let me zoom in here. Okay, so here I've asked it to add 4 to 6. So the computer is going to say, okay, that's fine. I'm going to start with 6. And then I'm going to apply the successor function 4 times. The first time, I've got I equals 0. I'm going to start from there. I got I equals 0, k equals 4, and equals 7. I've applied it once. I apply it again, I get 8. Apply it again, I get 9. And then I apply it again, I get 10. Now it's going to stop the loop because now I is no longer less than k, and it's going to return the number I got. So 1 to 5, how do we feel about that? How do we feel about what the computer's doing here? So what the computer's doing here, when I call this function that I've implemented to the computer called add, it takes n and it applies the successor function k times. Now, in order to do that, I need a counter. Now, I could use a for loop, but I want to use a while loop because it's more, in one sense, it's more primitive. Okay? So what I do is I set up an incrementer in memory called I. And then I have the number k in memory. And then what I'm going to do is every time I do, I start I at 0. And then what I'm going to do is increment I and k at the same time in this loop. So n is going to go up 1, I goes up 1. N goes up 2, n goes up again, I goes up again. So someone's asking, shouldn't I, as a programmer, use something other than k? Again, my goal is not to teach correct programming practices. Normally when you do loops, we do the third increment as k. This k is an input, okay? That's a very good point about the fact that my code does not read like code perfectly, right? I'm not trying to teach you best coding practices, although I try to practice them for the most part. But for me, having that k be the same k as the k in the notes is more important to me. Okay? That's a good question and a good thought. But normally I would, if I was doing this as code, I'd use different variables like a and m and stuff. But I wanted these variables to be the exact same thing that was in the notes. Okay. So again, what it does is it applies that length time. So when I call here 2, 0, notice here, it goes to 2, and then it never executes because 0 is not less than 0. This only executes if it's true. So k is the input to the function. These are the parameters on the function, right? So back to my notes. If I look back at my notes, right, k is that second thing. It's not an incrementer. K is the thing that it's one of the inputs to my function, and so is n. And so when I add n, right, I take n and then I add 2 to it by incrementing k times. And that's how the computer thinks of plus. By the way, this property right here is called commutivity. Okay. All right, so 1 to 5, how do we feel about it now? I'll go back up to the top in a minute. So I'm applying k. I'm applying the successor function k times to n. Okay. And you can't get it without playing with it in code. That's why it's an assignment. Okay, so now I've defined addition. Okay. So how do I do add in a computer? Well, I go I equals 0. So I have a function, procedure, taking n posant or natural numbers n and k as parameters. This is not perfect pseudocode. So if you're a pseudocode purist, you're going to be very disappointed with me because I don't care. When it comes to writing perfect pseudocode, the people over in comp sci will hate me, and that will be an appropriate reaction for them. I don't care. If they were over in my department and they started doing some of the things that they do in theirs, when their math notation, I would yell at them. Okay? So I'm going to take the natural numbers n and k as inputs. And again, we call them procedures. Okay? Or algorithm. Right? I equals 1. I equals 0. This will be my incrementer. And then what I'm going to do is I'm going to do while. And I'm going to do a while loop. While I is less than k, do the following. And I'm going to do n is assigned to successor of n. I is defined as the successor to I, and then I'm going to end loop. And then I'm going to return n. And then I'm going to end the procedure. So that's how to do this in a computer. If you want to see the code, it's in the exact code, PHP code in problem set. All right. I can even, if you want, what I'll do is I'll paste this to the notes because I know that some people are watching this that aren't in the class. How much I should care about these people is another question, but I do. So let's just paste the code right here. So there's the code. If I wanted it, I should clean it up if I'm going to stick it in my notes. But there it is. I'll put it in there. Okay, so now the question is, how do I do multiplication? So in one sense, addition and multiplication are kind, addition, I'm going to do k. Okay, so how do I do? So how do I do multiplication? Now, any questions, by the way? What is in the... Oh, that's an I. you were asking about. Yeah, that's an I. And again, you can see the code. Obviously, it'll be in the notes, but you can see the code also. I think you mean right here. Yeah, that's an I. Someone in Calc on their thing said that my handwriting was horrible. I actually worked on it for a while. It used to be a lot worse. One of the things that happens when you start teaching math is you start having to practice like your epsilons and your deltas and stuff like that, and your Fs. Have you ever seen like a mathematician when they write an F? Every mathematician, this is the sign that you're a mathematician. You have a pretty F. Because we write that letter so often, right? So every mathematician has his own little F way of writing the letter F. And if you don't think we practice this, we do. The other big thing, I learned how to. I had chalk initially. This is how old I am. So when you have chalk, you learn to write with chalk, and then we changed to whiteboards, and you have to learn how to write with a whiteboard. And now we're on this computer screen, and I have to learn how to write with on a computer screen, and I haven't quite gotten the hang of it yet. One of the problems was that I had bad nibs. Somebody told me that my nib thing had broken off, so I fixed that problem. Anyway, so how are we going to do multiplication? I want to define a function that multiplies to natural numbers. So what I want to do is I want to define mult as a function from n cross n to n. All right. Well, this one's hard. My first instinct would be to do this. Right? Because what I want to do, I want to take n and what do I want to do? I want to add n to it k times. Is everyone on board with what I want to do? Now, this right here wouldn't really do it. Because what does it mean? I've got, right now, I've got, what does this mean? Right? This would kind of say I did add n. So add of n. Right? Well, this first one would do n plus n. But then what does it mean to apply that to this, right? The inputs don't match. Because add takes two inputs and outputs only one thing. So it doesn't really work, does it? we had this solution that now isn't going to work, right? I wanted to find molt. Okay, so how are we going to do this? Okay. Well, this is one of those instances where the computer programming, before we do the math notation, we kind of have to do the programming. Okay. In other words, in this case, the programming, the pseudocode, what the computer would do, informs what the math does. Okay. And this is a common thing, especially in this class, but it's actually common to all 20th century math. Ever since we got a hold of computers, and even ever since we started thinking about computers, so think like Babbage, okay? It's been easier, a lot of problems are easier to do if you think about how a computer would do them, or in, the word was, the original term was how a ultimately efficient but profoundly stupid clerk would do this, because that's what a computer is, right? It's a perfectly efficient but profoundly stupid clerk. In other words, we want the algorithm. So it's easier to write the algorithm. Okay, so what do I want this to do? Well, if we use what I had before, right? Let's see. I can use an add function. Right? Let's define some what do you call it? Some specifications of our little program here. What do we want this thing to do? We want it to call add in some way. Right? What else do we want to do? We want repeated adds. Right? We want k repeated additions of n to our original number. Okay. And then we want molt of this is wrong. We want multiplication of nk of n0 to equal 0. So how do we feel about what we want to do, kind of 1 to 5? What we want to accomplish here. How do we feel about what we want to happen? Someone's put the philosophical question, aren't we all computers? Yeah, but you're a hybrid computer. You're both a digital and an analog computer. So your capabilities are a little different. Okay. All right. Well, let's start with what we had before. Let's start with a nice little while loop. Okay. So procedure. Procedure. Mult. We want it to take two parameters, n and k. Both natural numbers. Okay, now, if we take n and then add n to it, right, what would we like this loop to do? Well, let's look what we did before. What we did before was we had this kind of I equals 0. We're probably going to have a loop in the middle of it. And we're probably going to do something like this. So let's do that. Let's do an I equals 0. And let's do a little while loop. And it's going to need to run k times, right? Because I want to add k times something. Okay. So we're going to have an add. Now, what should I be adding? What should I start with? All right, where should I begin on my number lines when I multiply? If I start it, let's say I'm doing mult 3, 2. So I should wind up with the number 6. Yeah, so someone in chat has it. I need to start with 0. Right? I don't want to add 3 twice to 3. Because where I want to end up is 6. So what I want this thing to do is start here from 0, go through 3, and then go through 6. So it should do this. And 0, 3, add 3, 3. So I need a starter place. So I'm going to call that M. So this is going to point to where we are. I should have dot equals, by the way, here. I don't really care. All right. So if m is 0 here, and what I want to do is add this twice, what I'm going to do is I'm going to add... Oh, I no longer need an order pair. I'm going to add 0 as my initial. And I'm going to move over 3 times. So what I'm going to do is I'm going to start with m, and I'm going to move over k times? No. I'm going to move over n times. And then I'm going to call successor on I. How do we feel about that idea? 1 to 5. What I want to do, I'm drawing out what I do. I want it to add 0 to 3 and then add 3 to 3. So I'm going to start with 0. I'm going to add n to m. So n is what I want. N is what, let me put this. in this example, n equals 3 here. So the n becomes the k in add. The n came from a parameter. So I want to add n to 0 k times. So I'm going to add m to n, and then I'm going to have a successor I, and then I'm going to end the loop. Well, I did initialize it. So n was a parameter. It came in. So when I call m in n, right? When I call this function here, the n becomes the k in add. So m becomes the n in add, and k becomes the n. But that's fine because these things, right? This thing doesn't know what add does. Right? Let me actually move that up here and put it in things. No, it's not mult in m. The k is not useless. The k is the loop. The k is the controller of the loop. Okay? This had two parameters. So here, let's go back up to here. Here what I did was I called the successor k times. That's what I was doing up there. Now, what's going to happen is I'm going to call add k times. So in our example, mult 3, 2, I'm adding 3 to 0 twice. Yes, so n comes in as already defined, and so does k. Parameters means that I have n to start and k to start. Okay? So the parameters are n and k. This isn't a language, it's pseudocode. Well, but it's pseudo-ish code. So really what I want to do So how do I feel about that 1 to 5? Okay. All right, so we're out of time. Let me just go ahead and close this. I had to get through this in order for you to get to the problem set. But let me just finish this off. I know I'm over time. So in math, I define mult as a function from n cross n to n. All right, where mult of nk equals, so this is weird, add of, I want k to be n, right? So I want to do this. So I want n here. I'm going to do add, and this is going to be weird, right? I need add of add of add dot 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 add 0 n comma, because that closes that add, n comma n, sorry, comma dot 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 n comma n comma n. These are all like this. K times. Okay, and that is gibberish. And this is gibberish if you don't understand the algorithm. Okay? It is impossible to communicate what add is doing with this. Okay? What mult is doing. You can start it with you can do with add, you can kind of get this idea that I'm going to have repeated applications of the successor function, k times. But this is gibberish. The only way you'll understand this is if you understand the code, or understand the algorithm. Okay? There's no other way to really communicate what's going on. And that's part of the point, right? So when I say that, like, these coding exercises, right? Math is code. Code is also math. So they go hand in hand. You can figure out what's going on mathematically if you can write code for it. And you can figure out what to do code-wise if you can write it in mathematical terms. So they're not like, they're not like it's not like you have to understand the math before you can understand coding. Which is kind of how these books are set up, right? They're like, oh, well, you need to understand math before you can understand code. No, they go hand in hand. They're two lanes on the same road. And sometimes it's easier if you get in the other lane. And I want to make that clear. All right, I'm sorry about the amount of time it took. I wanted to answer your questions. Next time we will define, what didn't I get to? I'm almost 20 minutes over. We didn't get to the integers and the rational numbers, but I wanted to get to multiplication first. So next time, we will define integers and rational numbers. And And then we'll go over exponents. And then we may, hopefully we will, prove that there exists, if you have exponents and you allow their inverse, so if we allow inversing of exponentiation, we're actually going to create we're actually going to create the irrational numbers. Show that you wind up creating irrational numbers. Okay. Are there any questions? I know I'm way over time. I got... okay. So, resources to help for this problem set. Well, that's a good question. So, if you look at the problem set, I'm not saying that because I'm exacerbated, but I am saying look at the problem set. You will see all of these nice places where I put in documentation about the problem, about what to do. So, I linked to the documentation, and then I did something that I almost never do because I don't like to support commercial. Well, it's not that I don't want to support commercial things. It's that I don't like to link commercial sites in my thing that aren't like part of the code. I mean, in one sense. But I did do that here. So I put in links to things like W3 schools for a little bit of it, for like a discussion on what the new strong typecasting and stuff like that. But there's not a lot to do in what you're going to do in the problem set. The big thing is you're going to have to comment my code up like you know what you're doing. And then you have to implement the mult function, okay, to make it work. And I've given you some hints. You've got the algorithm. So the algorithm that I went over in class is the way to do it. Now you have to make that algorithm work in PHP. And make it work for yourself. And then there's some code at the bottom you have to uncomment in order to check it. So once you run it, you need to uncomment your code to see that it works. Any other question? Okay, I'm sorry. I'm now 21 minutes over. Okay. Well, thank you very much. And as I said, next time we will define integers and rational numbers. We'll get into exponents, and we'll create irrational numbers. Show that you actually have to create irrational numbers if you do that. Today we did revisiting the natural numbers. It's not helpful because I'm not looking at the camera, the tablet. Okay. So today we did revisiting the natural numbers. We talked about affinity. We talked about the successor function. I didn't do piano arithmetic. Oh, well. I sort of mentioned it. The defining the integers and multiplication. If there are any other questions, I will be hanging out a little bit. And that's it for today. Thank you. Sorry for going over so much. But you did need this stuff for the problem set.